In this video, I'm going to look at the importance of chirality in pharmaceutical synthesis. So when pharmaceutical companies actually synthesize molecules for drugs in the lab, it's possible for them to make both forms of the molecule. So what I mean by that is they can actually make both of the optical isomers. Now, often both of the isomers are made in equal quantities, so a 50-50 mix is known as a racemic mixture, and you would refer to each of the isomers as racemates. Now, for the purpose of A-level, you just have to have a basic understanding of how drugs work, so that's the level I'm going to pitch this at. Obviously it's far more complicated than what I'm going to say, but this is fine for the exam. So what I've got on the little whiteboard is I've drawn a chiral molecule, so you can see the carbon with the 4 different groups attached. So that would be our drug molecule, and underneath there we've got a protein structure. So that's a complex 3-dimensional structure which would be essentially made from amino acids, which are themselves chiral. So hopefully my diagram here can give you a sense of what the drug has to be able to do. We've got the chiral center with the 4 groups here, and you can see that this orange hexagon group is lined up with the hexagon shape in the protein structure. The green circle is lined up and the yellow diamond is lined up. So this drug is going to fit in the right way, it's going to fit into the protein structure, and it's going to have a certain therapeutic effect as a result of that. This desired effect that we want the drug to have on the body is known as its pharmacological activity. So if a drug is pharmacologically active, it will have the desired therapeutic effect. So let's imagine this drug has been manufactured in a laboratory by a drugs manufacturer. It's made both isomers, and so I'm going to replace this board with this board here. And I'll just put them side by side so you can see the protein structure is exactly the same. We've got the hexagon, the circle, the diamond. Hexagon, circle, diamond. So because this is the mirror image, we can see that the groups don't fit anymore because these two essentially are in opposite directions to before. So the yellow diamond is now directly above this hexagonal shape, and this orange hexagon is above the diamond. This won't fit, so this will be pharmacologically inactive. In other words, it's not going to have the desired effect. You can see I've underlined the word desired now, and that's because these mirror image molecules could have an alternative effect, an undesired effect, and that they can often lead to problems. So when drugs manufacturers make these drug molecules, it's really important that they only contain the pharmacologically active form of the drug, because the inactive form or the mirror image form could have harmful side effects or non-desired effects. I'm going to focus now on a molecule that I'm sure a lot of people will have heard of, and that's methamphetamine. And so I've got the molecule model there, and hopefully you can spot the chiral center. Let's give you a second to find it. So it's this carbon here. So you can see we've got 4 different groups attached to this carbon. We've got a hydrogen, we've got a methyl group, and we've got this CH2, then the benzene ring, and we've got this NH group with a CH3, a methyl group on the amine group. So chiral center, therefore this molecule can exist as a pair of optical isomers. It's only got one chiral center, so a pair of isomers, two isomers. And now I've drawn up my clockwise and anti-clockwise arrows to show the two different effects on plane polarized light. So the form of methamphetamine that rotates plane polarized light in a clockwise direction, so that's the dextrorotatory form, that is the molecule present in crystal meth. And we all know from Breaking Bad, if you've watched it, the effect that can have on the human body. If you just swap two of the groups around on the chiral center, we end up with the anti-clockwise form, or the levorotatory form. That molecule is present in perfectly legal substances. You can buy them over the counter in pharmacies, and that's present in nasal decongestants. So the production of a single isomer, and that's known as an enantiomer substance, production of a single isomer with the correct pharmacological activity is going to have advantages over a drug that has both isomers present. So the first obvious advantage is it reduces the risk of any undesirable side effects, and it also allows a reduced dosage because the drug is far more effective if it only contains the molecule or the form that's going to cause the desired effect. Now sometimes the mirror image won't cause any problems, but obviously if you've got that there, if you've got that present, you have to be sure that it's not going to cause any problems. So it's obviously a lot more, a bit better peace of mind, if you like, for the drugs company to get rid of it. And of course another reason you could give is if you produce a single isomer, there would be no need for any expensive separation because you've only got the form of the drug, the form of the molecule that you want. Why is the separation difficult? You can see I've written in red there. It's difficult because optical isomers, because they're essentially the same thing, they've got the same structural formula, they've got the same physical properties, or very, very similar physical properties as a result. So their melting points are going to be the same, their boiling points are going to be the same, their solubilities in solvents are going to be the same. So very, very difficult to separate. The second method we can talk about is called chiral pool synthesis. So chiral pool is basically a stock of chiral molecules, often naturally occurring molecules, which occur as the single optical isomer. So they would have the inbuilt or the desired chirality that you need in your final drug molecule. And I've just put a couple of examples up there of some naturally occurring molecules. So we could be using alpha amino acids or sugars. And the third and final example I'm going to talk about is transition metal complexes. So some transition metal complexes actually exhibit optical isomerism themselves. So they can be used as what we call chiral catalysts. And again, similar to the enzymes at the top there, the chirality in the catalyst is transferred into the product, and so you can end up with the chirality that you want in your drug molecule.